Hi, my name is German Zuniga Ramirez. I'm an undergraduate student at California State University of Fresno. My research topic is on very long instruction word architecture, also known as VLIW. My research is focused on how VLIW architecture is used in embedded systems. Due to the growth of the Internet of Things, the demand and the need for embedded systems is increasing. Embedded systems are being used in a great variety of applications, such as digital signal processing, image processing, uh, sensor networks, wireless communications, cellular phones, etc. They're being used everywhere. Also, the complexity of these systems is increasing because of the more and more functions they are offering to the user. Every day, these systems offer new functions to the user. For example, refrigerators now offer internet access to the user. Also, the user is able to play music, play radio, or watch TV on a refrigerator. These increasing functions being offered to the user require systems with enough processing capabilities to handle these tasks. Therefore, we have to find an architecture that provides the required processing capabilities, and this architecture is VLIW. So what is VLIW? Well, VLIW architectures are alternative designs to superscalar processors. Superscalar processors exploit instruction-level parallelism through very expensive dynamic hardware scheduling. And like superscalar processors, the main purpose of VLIW architectures is to improve a processor's performance. VLIW are used to achieve a higher performance by being able to execute multiple operations in a single clock cycle. Also, like superscalars, VLIW architectures exploit instruction level parallelism. However, they do it through the compiler instead of using extra hardware resources. In VLIW, the compiler reduces the program instructions into basic operations that the processor can perform at once. These operations are then included. Um, these basic operations are then included into one very long instruction word that the processor then takes apart and passes the operations off to the appropriate execution unit. Figure 1 here shows a generic VLIW instruction format. Based on this instruction format, this architecture can perform 4 operations at once. So this encoding done by the compiler leads to a dramatically reduced hardware complexity compared to other higher degree superscalar implementations of a RISC or SIG architecture. As a result, a big advantage of VLIW is that its implementation is much simpler and cheaper to build. Figure 2 here shows a generic VLIW implementation. This architecture uh, has 4 execution units, and it shares a register file, data cache, here's our instruction cache, and instruction register. This is just a simple architecture, generic architecture. Um, VL, uh, VLIW architectures moves the complexity from hardware to software, and usually it is easier to handle complexity in software than in hardware. Uh, Also, this trade-off has one more benefit. This complexity it's only paid for once. It is only paid when the compiler is written instead of every time the processor is fabricated. This is one advantage of BLIW over superscalar processors. Um, why are BLIW architectures a perfect solution for embedded systems? Uh, BLIW architectures provide a much simpler hardware design. As a result, we have a lower hardware cost. Also, we have a low power consumption, which are perfect solutions for embedded systems. Uh, and we can conclude that BLIW architectures provide a high computational power on a reduced hardware complexity and low hardware costs. So this is why BLIW architecture is an attractive solution for embedded systems. Now I'm going to discuss and analyze an example of a BLIW architecture. An example of a BLIW architecture is VEX, VEX. VEX is a compilation simulation tool system that targets a wide class of BLIW processor architectures. It enables compiling, analyzing, and evaluating C programs for a BLIW processor. It allows to selectively change the compiler target and many simulation parameters. VEX has three basic components. One component is the VEX instruction set architecture itself, which defines a 32-bit cluster VLIW IS8 that is scalable and customizable to individual application domain. It allows changing the number of clusters, execution units, register, and latencies. The other component is the VXC compiler. The compiler uses trace scheduling as its global scheduling engine. It selectively exposes some of the parameters to allow architecture exploration by changing the number of clusters, the number of execution units, issue width, and operation latencies, without having to recompile the compiler again. And the other parameter, which is the uh, the system itself, the VS16 simulation system. Uh, this image here shows the default VEX cluster architecture. The default VEX system has two register files. The register files, this is one register file, which consists of 64 general purpose 32-bit registers and one eight, and this other register file it has 8 registers, 8 1-bit branch registers. The system has 4 LAUs, which means that the system can perform 4 operations per instruction. It has two 16 times 32-bit multiply units, which are these two here. The system also has a data cache, a four-way data cache. Also, the system contains a control unit for program sequencing, which is this is our branch unit. Uh, all these parameters are customizable. They can be customized depending on the need of the system that you need to design for your purpose. What embedded system you want? What is the purpose of your embedded system? So this can be customizable. And another feature of VEX8 is that it supports multi-cluster, where each cluster provides a separate VEX implementation. Now I'm going to talk about trade-offs in VLIW architecture designs. Like any other engineering choice, uh, BLIW architecture offers trade-offs, or there's trade-offs between different design parameters. Customizing or scaling these parameters offer us trade-offs. Nothing is for free. Uh, One of the main concerns in the design of multi-core systems is area efficiency. The systems have to be designed such they are efficient in performance and as well as in area. Um, One of the main issues when designing a system from scratch is choosing the right size of the register file and the right amount or the right number of execution units. Um, just choosing a higher number of any of these, it might increase the performance of the system, but at the same time, it might increase the area and the power dissipation. And this is an experiment I'm trying to conduct right now. I'm trying to use the VEX uh, architecture discussed previously, and customizing and scaling the components or the parameters of this architecture, and see what's the output performance of these different uh, configurations, the different designs. And this is my work in progress right now. And this concludes my presentation. Uh, the next slides are just references where I'll obtain my information from. Uh, this is it, and thank you very much.